Okay, good afternoon, everyone. So we'll begin the third session of the day, and I will ask for the speakers to come. Please, Piero Baglioni, if you can come to the table. Bronwyn Ormsby, Atina Georgia Alexopoulou, and Balázs Lenz. I'm not sure how to pronounce your name, sorry. Okay. So we'll begin with Piero Baglioni, who's Emeritus Professor of Physical Chemistry at the Department of Chemistry at the University of Florence. He is the author of 27 patents in the fields of colloids and also the founder of the CSGI Research Center for Colloid and Nanoscience, together with Professor Ferroni in 1993. And he also worked in this research center on nanorestore gel. He will present now new green and sustainable materials for the wet cleaning of works of art. Thank you.
Okay, so thanks a lot, and thanks to Antonio and people from the Quai Branly, because there's numerous persons, for organizing this nice event. And even for the lunch. Now this makes me a little complicated speaking just after lunch. Even okay, so we try. So new green and sustainable materials. So why new green and sustainable materials? So the problem is that this subject we start some time ago working in a new methodology for conservation, just to get new materials, different materials from classic materials used in conservation. And then we were happy because and lucky because European Union decided to support this field of science, say. And then they, just to mention the project close to us, they funded NanoRestore, Nano4Art, Innova Concrete, Apache, and then this GREENART. So during this period, which is about 15 years, we formulated many new materials that in part they are available, in part full, totally available to conservators if they want to use. And they are based on formulation for cleaning formulation, so cleaning fluids that in gels and also in organo or hydrogels, and then also in other material for strengthening or deacidifying, for example, in the case of paper. So how were these materials? They were good or not from an environmental point of view? They were tested actually by European Union through a body they use, that is Solar Impulse Efficient Solution, which is based in Switzerland. And then what came out is that if you look here, this is the benchmark actually, so this is the level of the benchmark, and this one is the solution we propose. So we have a strong increase, for example, in environmental footprint, in the climate change, so our solution basically doesn't change anything. They don't affect the climate change. And we don't produce, for example, CO2 compared to the main solution. And from the health point of view and the ecosystem, you see that these are our solution, and this is the benchmark. So this solution we already developed were pretty good, actually. They would be very safe. So, but the idea is that you have to move, and to move in a different way, different concept of production, industrial production, so to protect the environment. This is an old idea, and chemistry actually was the first that contribute, contrary to what is thought, and people are thinking that chemistry is bad. Chemistry is very useful. Without chemistry, this world cannot be rescued from. And this came in 1990 when with the first document we have to prevent pollution and to protect, say, environment. So chemistry at that time started producing some principle we had to follow in chemistry to produce or to just rescue environment that are compromised by previous, previous aggression. And this depends on how you produce materials. So this is the 12th principle of green chemistry. So now, the idea was, in the last project in GREENART, was to move to full green system. And that's Martina in the morning explained clearly what is the path we have to follow in order to get these materials. And then if you stay for the workshop tomorrow, you will try to understand better, and you will play with Andrea Cassini or Poggi on how you can recognize the right solution, how you can calculate and see what to do. So this is what Martina was saying in the morning. So we have 3 steps, roughly, that are related to the safety dimension, and then you have environmental dimension, and then you have to check if what you propose costs about the same or not. And if it's too expensive, it's difficult to propose. So the project GREENART is based on this idea. So to have something that is fully, more or less fully green. This doesn't mean that the solution of GREENART are better than the solution we had in the previous. So that we are trying to adjust, but sometimes it's not so easy. So some are better, some are not better. So this is the partenariat we have in the project. Is quite large. It involves 3 institutions in the United States, 2 in Brazil, 1 in China, 2 or 3 in Japan, and so on, and most Europe. And so what we are doing and what we did, we work with safer solvent, polymers, monomers to produce polymers, surfactants, and conservation methods. And what we have now is something that is clean, sustainable, and safe for artifacts and for restore, mainly for restore, even artifacts. So the GREENART actually outcome is a cleaning system, protective, coatings, consolidants, packaging, and solutions. So this is GREENART. You had some bite in the morning, and then you will have later. So more or less on this, you can classify in this. What we have now, we have many solutions that are already in. The project is going to the end, but we have many new materials and new methodology. And if you're interested, we can discuss later after this talk. So I'm going to say something about cleaning, because this was my they ordered to give something on cleaning, so I'm obeying to my boss Antonio, and cleaning. So cleaning, what is cleaning now? Cleaning, there's 3 main systems for cleaning something. You can use pure solvents or mixtures for cleaning. And from this point of view can be strange, but water is the best solvent for cleaning. So I know that some of you don't like to use water, but water is completely the most important and the best system to remove materials, to de-wet materials. And if you don't want to use water, you can make something more complex using surfactants that helps for different solution and complex fluid that we call microemulsion. We use microemulsion, but we can use also something else. And then we have gels, and we use gels as containers, so with different purpose of gels, and we will see. Wow. So basically, we use for cleaning hydrogel, organogel, cleaning fluids that can be nanofluids or nano-structured fluids, and these are the main, say, palette that we have, we can use. So what does means cleaning? Cleaning means do something that is the reverse of the adhesion process. If you have dirty, means that the dirty deposited stick in some way on the original layers that then you have to remove. So from chemistry and physics, there's a parameter that describes very well this. Is called spreading coefficient, this parameter S. So you have to follow, you have to check how big is these parameters and the sign of these parameters. So you can have S greater than 0, you have a total weighting or partial weight and total de-weighting. So if you know this and you play with this number, actually you can clean partly, you can deposit something or remove completely. This is what you can do. This I don't know because I don't know. There's nobody there. Can you push on this image with the... No, okay. There's a movie. Usually I use my computer, so in this case it's more complicated. So here what you see the difference from solubilization and to remove the materials using okay, this is working. Okay, so you see here, you solubilize. If you see this hole, means that some materials, that in this case is paraloid, has been removed. And this is removed in a different way, the paraloid, you see. This is actually much better, as you see here, than if you try to clean by solubilizing. So when you want to remove something, you have to try to remove in the second way and not in the first way. This is another example. Here you can remove a layer, and this is an acrylic over another acrylic, and you can remove all the acrylic layer in red over the black. So these are the solution you can use, microemulsion, solvent, and so on. But if you want really control the cleaning, you have to go through the confinement of these materials into something, and we use actually gels for confinement. If you use gels for confinement, basically you can control completely the liquid that you have into the gel. So which liquid we are using in the new formulation? So these are the classic system for cleaning that are different microemulsion that roughly cover most of the most of the materials that you want to remove, so they interact in different way, and these are a classification of solvent, for example, that you can use and replace the other solvent. So if it's green, means it is good from a health point of view and from chemical point of view. And if it's red, means that it's bad, and it's better if you don't use it. The yellow is something in between. The same for surfactant, for example, for the materials that you need to produce this microemulsion. There's some surfactants that can be used and that are fully say green. Some other, there's only a few. Some other are not very green, but are not even bad, so it's okay. So then what you do, if you want to build new system, you make a table with the solubility table, and then once you know who for example, is good for paralloid, for paraffin, for dammer, and this is just a table that tells you which solvent you might use to build up your system. What happened during this project that we realized some new systems, some new microemulsion, and these are tests we did, and the new microemulsion that we have formulated are these 1, 2, 3, 4, 5, 6, 7, 8. We have more, but these microemulsion are fully green and sustainable, and they cover more or less the same. So these can replace the 4 or 5 microemulsion I showed you before that were not fully green. So these are the microemulsion. If you want really control what you want to, the cleaning process, you have to use gels. Why you need to use gels? And we use gel, but we use mostly only chemical gel, or gel that behave in a chemical way. So means, why? Because we need to control the tridimensional structure, okay, the 3D structure of this gel and the dynamics of the gel, because when you load the gel with the fluids change his behavior according to the gel. So they interact with the gel. And so you have to control the topology you have into the gel. And then if you control the topology, you control the dynamics into the gel. For example, if you have a gel, you have porous structure, and then you want to remove, and something that you want to remove goes into the porosity, or something that you have into the gel goes in the layer that you want to remove. It's something like that. So you have a solvent molecule or a solvent that come out from the surface that has to pass through in one way or in the other way from the gel. But this is an example. When you have a pure fluid, you have something like this. So it's a full system, is not partitioned, I'd say. It behaves all in the same way, but when it goes through the gel, you get individual droplets that behave in different way because the high surface, say, area you have in. So what is control? The capacity of cleaning of the gel is related to the porosity of the gel and how this porosity is interconnected into the gel. These are examples of gels that you can use. You will see later. So we have a scaffold. We can add the solvent. And if we have this, you can control the diffusional properties of the embedded system. So basically what you do here, you can control a parameter that is called tortuosity. And this tortuosity tells you many things about the cleaning process, but in particular it tells you how long a water molecule, for example, or a molecule of solvent stays on the surface, so interact with the surface. So this is an example of how you can change the tortuosity here, this tortuosity. You just change the structure. And this is an example, typical example, if you change the tortuosity here, you see, depending on the tortuosity, you can, exactly the same gel, you can clean in a poor way, in an average way, or in a good way. And this is the same stuff, but different tortuosity. So different residence time. So what can you do this? I can maybe skip this. You can do this, for example. If you have these things, these gels, you can do something that is difficult to do in conventional way, like, for example, this one. So this is acrylic over acrylic, is a Banksy. And it was completely difficult. It's almost impossible to remove the red from the original, because if you try to remove the red, you remove also the original, exactly the same composition. So if you use a conventional solution chemistry, it's almost impossible to remove the red over the white in this case. So this is just an example of what you can do with this new methodology. And this is what you have now, is just one part of the Banksy that is in New Orleans. This is another example coming from the Chirico in Peggy Guggenheim, and this you can see is the area that has been cleaned, simply touching the surface for a few seconds. I guess that Browning and the other have much more, many more and better examples to show. So that's, I hope you have a more general, I'm done, I'm finished. More, don't be so anxious. Okay, so, and this is an internal test by Cassini that he showed me this internal cleaning test in the lab. So what can I say? Within these 15, 20 years, there was many people that cooperate and help in define this system. And there's an impressive number. So these are only few names, but there's many other that cooperate with us during time. And okay, I thank you.
Thank you very much. Now we will have Dr. Bronwyn Ormsby, and she is the Tate's principal conservation scientist. She manages the conservation science and preventive conservation team at the Tate's since 2016. She is a specialist in the analysis of synthetic polymers and modern paints. And some of her research projects were focused on new green options, like the Rothko research project on surface cleaning treatments. And she will talk now about evaluating and assessing novel cleaning systems for the cleaning of works of art, green art at Tate. The floor is yours.
Thank you very much for the introduction, and it's lovely to be here. So, as has been described, I'm going to speak about the Green Art project that we've been fashioning at Tate since the beginning of the project. And I'm going to be thinking and expressing a little bit about the methodology that we've used, as well as some of the key results. So, some of you may know we were a partner in the Nano Restart project, where we cleaned two of our mid-20th century icon pieces with the Peggy gels. And so we were quite keen to explore the new green versions in the Green Art project. So when we were thinking about how this would work for Tate, it was quite clear to me that we needed to think about a British artist this time, and also someone who is still around and could have conversations with us about her art. And so we focused quite quickly on Bridget Riley, who's a British painter who's still around. She's 93 years old, and a lot of her works from the early 60s to mid-1960s are now coming up for conservation treatment for the first time. And both of these works have been flagged for cleaning for some time by the painting conservation team. I'll talk more about the paintings. For one is Fall on the left from 1964, and on the right is Hesitate from 1963. And here's Bridget Riley. You'll see her again in another slide. Of course, the methodology, as everyone's familiar with, involves looking at the art historical context of the artworks in order to inform the conservation treatment decision-making process. And whether we go ahead with cleaning or not is of course dependent on a number of different factors. But certainly looking at where these paintings fit in her oeuvre and what she was trying to achieve with them was deeply important. Then, of course, as everyone does, the conservation records. Actually, Fall's been in the collection since it was painted effectively, and Hesitate came into the collection a little bit later. So there is a conservation history in some senses. There's certainly a display history for both of these works, and we have very extensive condition reports. Not much analysis had been done, but we also have quite a few artist interviews with Bridget Riley herself, which we also, of course, explored in order to inform the treatment. And here she is now. This is last year. She was brought into Tate very quietly to look at the two paintings that we were considering for the project. And she spoke for 3 hours eloquently about her practice and her influences. Very little on the technical detail, unfortunately, but she was delightful to meet. And in the middle picture there is the guy in the blue shirt is Phil Young. People might know him as a private conservator in London, but he's also Bridget Riley's conservator and chair of the Bridget Riley Art Foundation. So we had Bridget Riley's representative involved in the project from the beginning. And there I am, not standing too close because she's one of my heroes and I might fall over. Of course, then proceeding further, and all of these things happen in parallel, of course, is examining the works of art very closely, using conservation examination techniques, established ones, as well as some portable scientific analytical instrumentation and imaging instrumentation. And you can see various types of analysis and microscopy happening there on the left. And on the right-hand side is the more sort of bench instrument we have access to at Tate these days, thanks to a bunch of British government grants. So these are the techniques. I won't go into detail because we don't have time, but they're the kinds of things that we use to sort of evaluate or understand the materials and then evaluate the treatment. Here's an example of a cross-section. You can actually see the structure, certainly, of Fall is very simple. They are both painted on hardboard, which was a very particular type of hardboard made in Sweden. And the white paint actually forms the priming layer and is applied at the consistency of single cream, according to Bridget Riley, in a number of layers on top of the hardboard. And on top of that, in the top slide, there is, I think, a black paint at the top, and in the bottom there is a black paint, followed by a very thin layer of white paint, which are artist's adjustments that she made in order to confine the black lines that she created. Some always have to have an infrared spectrum or two in a talk, so here's the examples this time. They're both polyvinyl acetate binder, fairly simple paints actually in lots of ways. The white, which was actually a brand that I haven't been able to find much out about, called Della Robbia. Titanium white, kaolin, barium sulfate, the usual culprits in modern paints, and the black is actually a Rippolin polyvinyl acetate paint, which we're investigating more in a slightly sideways project. Because the Rippolin research so far is focused on the earlier resinous paints available to artists. So the black paint is bone black, chalk, kaolin, and talc, and there's also some iron oxide black in there as well. So relatively simple constructions. Pyrolysis GCMS, of course, far from simple if anyone's used it, but this definitely confirms polyvinyl acetate, and also we were quite interested in the plasticizers and other additives in these paints. Because they haven't been looked at hugely in the conservation field in terms of conservation treatment risk. So just to summarize that part of the methodology, they're both polyvinyl acetate paints. They're both on hardboard, which are single sheets of hardboard that she commissioned on purpose from a Swedish hardboard maker. The paints were chosen deliberately. They're both house paints, and she went out and found both of them and tested them and settled on these two colors from these different brands. In terms of condition, we did some preliminary cleaning tests, and we didn't get much on the swabs, but we knew there was an ingrained surface dirt layer on both of these works. And the soiling, certainly at Tate, seems to be kind of grey-yellow, quite tenacious soil, especially for works that are fairly constantly on display. and these works were the same as the other works we've cleaned. Water-sensitive paints, because they're polyvinyl acetate, and I think the biggest risk was they're pressure-sensitive, so any kind of pressure on the surface causes the gloss to change quite markedly. So just some science. We were lucky enough to have a scientist for 2.5 years as part of our project, and she's been in the background doing various bits of analysis and explorations of polyvinyl acetate paints, and so you might have seen this paper already. It's published and available on the GREENART website, just looking at kind of the conservation concerns and the analytical history of polyvinyl acetate paint research. And now we're just about to publish a paper on a pyrolysis GCMS method to identify the plasticizers. If you're interested in that, it's coming out soon in the Journal of Analytical and Applied Pyrolysis. It's just in the final review stage. So what some of the things we're looking at in the papers was the solubility of some of these additives because of the risk of extracting them in cleaning treatments, and we also did your classic 24-hour extracts that scientists love to do, including myself, to see what kind of materials might come out of the paints, while acknowledging it's nothing like touching the surface with a beautiful sponge-like water-based system. It did tell us, and tell me in particular, that the additives are very similar to those that are vulnerable to extraction with acrylic paints. We also did some swelling studies. There's not been a lot done on polyvinyl acetate paints, and we used the Franken-Bourgeois paints because they're the only really available ones to us at the time. We tried to get bespoke 1960s PVA paints made, but they are not possible because of the phthalates that are in them. So we used a microscopy technique, based on Stefan Zumbel's technique, published in Modern Paints Uncovered in 2007. We went through a whole bunch of pH and conductivity adjusted waters, as you do, to look at the swelling curves, and the black paint had a higher swelling profile than the white paint, and the aqueous systems did produce some difference between, for example, deionized water at the top and 6 millisiemen pH 5 water at the bottom of that group at the top. And again, at the bottom there, you've got 2 hydrocarbon solvents and a silicon solvent, which didn't cause much swelling at all, which is kind of what we expected. But these results did inform the aqueous system we used with the gels. I won't dwell on this because I'm sure I will overrun time. Just to point out that the white paints had far less distribution in terms of their swelling response, so it didn't seem to be so important for this white paint to have a particular pH and conductivity, whereas it did very much the case for the black paint. And again, that's the difference between pH. If you look at the curve on the right-hand side, pH 5 and 6 are really close for the white paints, but for the black paints, we were thinking we were starting to see some shrinkage in the black low pHs, which is probably the dissolution of the chalk in the paint. So from that, obviously, we went back up to pH 6. So making mock-ups, we all love making mock-ups, and here are some nice examples of mock-ups that fit into our aging chamber, which is why they're the size they are, using different elements of both of the paintings, design elements, plus black, pure white, and gradients of white to black, just to mimic different aspects of both of the paintings. They were aged, then they were soiled using the soil that people call Tate soil, but was originally a paper from Richard Wolbers in the 90s. Modified a little bit and used a spray gun, not a varnish spray gun, just a spray brush. So then, of course, comes the Excel file nightmare of trying to carry out the assessments, starting off with rough mock-ups, then moving on to the painting mock-ups, taking the best systems to the painting, going back to the mock-ups, and then again to the painting and optimizing the cleaning system. That's pretty much how it worked for us in the Nano Restart project, and it also worked in the same way for this project. I'll give you some of the results now. For those of you interested in what we trialed, we haven't tested everything. We were very much in the aqueous cleaning space, as Piero said. It is the best cleaning system. So we were looking at pH and conductivity adjusted waters, addition of surfactants, addition of citrates, for example. Is that me being late, or is that your phone, Piero? Oh, I'm all right. Okay, good, thanks. Didn't know it was an alarm. We looked at what we're calling spreadable gels, so those gels that like xanthan gum, etc., that need some kind of mechanical action and clearance. Then the group of CSGI gels, including the PEGIs from last time, as well as the more rigid gels that we know, agarose and gel and gum. And then this is the list of the GREENART gels and the CSGI gels we also evaluated as part of the project. And you can see, as Piero mentioned, the decoration of the sebacic, adipic, and serberic acids into the gels, and we put them through their paces. This is a pure white cleaning painting mock-up, and you can see the way we were doing it in a fairly systematic fashion, writing results, and we also created style diagrams to capture a number of parameters at once, which I think most of the GREENART teams are using now. Here's the black mock-up. Very difficult to image these, as you can imagine, but we tried. We found raking light, as conservators would know, to be the most useful. And here are some examples of star diagrams. This is just 3 that I've cherry-picked for you. On the left-hand side, we have a number of free liquids with cotton swabs, your classic way of cleaning. In the middle, we have the same systems with some of the CSGI gels, just with deionized water for 1 minute. And then on the right-hand side, we have the tailored CSGI gels, which are generally the new ones, with triammonium citrate and EcoSurf in the low amounts. And the general gist of these is the larger the shape or the larger the star, the better the system. So you can see there's an improvement from the left to the right-hand side as we tailor and test these gels and aqueous systems. Unfortunately, this painting does dreadful things to your eyes, so it's very hard to actually see what you're doing. But hopefully, particularly I think in the middle one, you can see this is a cleaning test on the painting with actually the system we ended up using on the painting, which we finished cleaning about 2 weeks ago. On fall, by the way, sorry, not hesitate. You can just see perhaps that the white paint is far whiter, and that grimy greyness and the yellowness of the Tate soil, the real Tate soil in this case, is definitely starting to lift. And this is us, again, tailoring. This is the final stages of the tailoring. I call it the optimization phase, where we've decided on the aqueous system. We've worked around the pH, conductivity, citrate, chelator, surfactant space, and we've arrived in a good, efficacious system, and we then matched that with the best gel, hydrogel possible, and we've come up with the optimal system for that particular artwork. So maybe you can see some cleaning tests there. In the end, with the help of the CSGI team, we were working with the second versions of the succinic, is it succinic or suberic? Succinic acid gel, and also the sebacic acid gels. Yes, hopefully you can see there on the slide in the middle, there is the kind of the dirty part. And what we were doing here was looking at the difference between EcoSurf EH6 and EcoSurf EH9, just to make sure we picked the right surfactant for the job. And we ended up using EcoSurf EH6 because it's a little bit better at removing oily soil. So this is the actual cleaning treatment. It took us, I would say, probably all in all, with all the testing and all the analysis, over a year to get to this point. But we are doing it incredibly systematically for the project. So this commenced, I think, in early March, and I just wanted to talk through how the conservation team actually worked out how best to apply the gels to this artwork, because every time we've used them, we've done it differently. We've had to do it differently because the paintings have a different risk and the soiling layers are different to some extent, but they're also adhered to the painting in different ways. So this is a net. If you look at the image on the right-hand side, that's Annette King, and we have Katie Mary Twitchett Young on the other edge of the painting, and they are working together. One thing I would say about using the gels and the way that we use them is it's definitely a 2-person, if not a 3-person job, because you're doing 2-minute exposures and there's quite a turnaround of application, cleaning, blotting, all of those things. And you have to have quite a well-designed system of gels in pots and different cleaning systems. So there's quite a bit of planning involved. So what they're doing there is they're using templates of mylar, which we decided to use with this work, which we hadn't used well, we have used mylar templates quite a bit actually, but not always. And we originally hoped to follow the design, the snaky lines of the design of the artwork, but we ended up not being able to do that because the gels weren't quite big enough for that. So we ended up making our own curvy line so as to not introduce straight lines into the composition when you're cleaning. So they've got 2 curvy mylar templates and they're putting 1 gel on at a time. And then what they're doing with their hands there is they're just gently massaging the gel to get rid of any air bubbles. They're leaving that on for 2 minutes, quite handy to have a watch you can talk to time you. And then after that, they let it dry, just very lightly dry, and then they applied a clearance gel, which is deionized water only, for 2 minutes. So the same exposure for the cleaning gel and the clearance gel. And then they moved along each line. I think there was probably about 14 different lines across the painting, and I think we used about 70 gels across this work. This is just to show the removal of a drip mark, and hopefully you can also see the increased white, the coolness of the right-hand image as opposed to the one in the middle, which is a little bit yellow. You can see the drip mark is being completely removed. And these paintings were covered in those kinds of museum spatters and drips and marks and spots. So on this particular screen, we have mid-treatment UV shot. The darker side is the clean side, and the fluorescing side is the dirt remaining on the surface. Unfortunately, the artwork is in the photography lab now, so I don't have an after-treatment shot, but you wouldn't be able to see any difference anyway, because this is very subtle. Plus also the composition, the design is very hard on the eyes, and it's very hard on cameras, and it's very hard on microscopes as well. However, maybe you can see on the right-hand side, this is the edge where we have some pure white paint, and you can see on the left-hand side where you've got a clean section, and on the right-hand side where it's still a bit grubby, and there we are cleaning her signature. Not off, but just to clean it, just in case you were wondering. This is not a very attractive version of this schematic. I will improve it, but I like to present this to conservation audiences to show our thinking process as we move through all of the options in the wet cleaning space. So if you follow it from the top, we have wet cleaning versus dry cleaning, and there's a red X next to dry cleaning. We ruled that out because of the inability for this painting to take pressure. So that also meant we ruled out a lot of systems that involved manipulation and or swabbing and or clearance steps, which is one of the great things about these gels, and one of the things that we find most attractive about them at Tate is the lack of mechanical action. And they're also incredibly efficient at picking up soil when you find the right way to use them. So we're in the aqueous space, and we, as you know, we looked at the pH and conductivity of the waters. We got to pH 6, so pretty much where we are with acrylic paints as well. And of course, as Piero was describing, confining the liquids is always helpful, and it certainly was helpful for this artwork. We ruled out what I'm calling spreadable hydrogels because of the mechanical action involved, and we ended up in the gel space. And eventually we ended up with the succinic acid version number 2. Thank you. This is the last slide. Hey, I did all right. Okay, ongoing work. Of course, this isn't quite finished. We are also working with CSGI and carrying out our own residue studies on the mock-ups, just to see if anything's left behind, and if it is left behind, then we will struggle with working out what that means and whether we can optimize any of the clearance. We're looking at the painting surface again after treatment with various techniques, and I just did colour and gloss measurement last week, but don't have the data at this point. And we are also hoping to clean hesitate next, unless it starts behaving incredibly differently, because we might run out of time. But I'm imagining that all of this work will extrapolate quite nicely onto that painting as well. So hopefully by the time we get to the London training event, I'll have more to say on hesitate as well. So thank you very much for your time, and thanks everyone for the conference.
Thank you. Now we will have Atina Georgia Alexopoulou. She's a professor at the University of West Attica and at the Department of Conservation of Antiquities and Works of Art. She's also the leader and founder of Research Lab Articon that promotes visual art, book, archival materials, and conservation about these works of art. And she's specialized in chemical microanalysis of works of art, non-destructive diagnostic methods, sorry for my English. And she will present now a proposal of user-friendly methodologies for the evaluation of green materials.
Well, thank you very much for being here. I'm very happy being among you, and please allow me to read my text to express what I want and not what I can. So, imagine stepping into a world where art restoration is just about preserving the past, but doing so sustainably, responsibly, and with cutting-edge technology. That's the world of the GREENART project you have the chance to hear about from Professor Baglioni and previous speakers. And I'm happy to share with you our team's experience in evaluating these groundbreaking green solutions. Okay. As you can see, we are diving deep into assessing everything from green cleaning fluids and gels to protective coatings, consolidants, and even packaging materials. And we're not just stopping there. We're also involved in validating and testing sensors in both controlled and real-world environments. But our way to do this is oriented to propose an easy-to-handle methodology. Now, the heart of conservation restoration lies in answering a critical question. Did our treatment work? Was it the right approach? Are the appropriate materials used? Which is the impact of our treatment on the project? This is where our team, our Articon Lab team, comes in. We are not talking just about lab results. We have to consider practical, accessible solutions for everyday restorers. This is the core of my contribution today, so I will try to present our work in the base of our experience gained within the project so far, as well as within our education and research activities. As you can see, our work focuses, among others, to propose and promote user-friendly methodologies of everyday use in restoration practice. Think about it. While advanced labs with high-cost equipment offer incredible insights, not every restorer that has that luxury. What if you are on site facing a delicate artifact that can't be moved? What if sampling is out of the question? What if a quick condition assessment is needed? That's why we're proposing user-friendly real-world methodologies that can be used right on the spot. This brings us to non-destructive testing, shortly NDT. We've built years of expertise in this field, and we believe for good reason. NDT is a green method technology, environmentally conscious. Think minimal waste, low energy consumption, and no need for sampling. It's user-friendly. Imagine being able to see beneath the surface, to map materials and detect minute details, all without harming the artifact. It allows for in-situ applications, providing immediate results in situ. We are talking about paintings, frescoes, archival materials, ceramic, stone, metals, almost every kind of artifacts. The possibilities are quite wide. It also offers the possibility to have serial checks. For example, examine a large number of pages of archival material or a collection of similar objects. NDT can also be used for monitoring the evaluation of deterioration or the damage. NDT is then green, fast, reliable, economical, and safe, especially crucial for those delicate, high-risk pieces and structures. But let's be real. NDT is not perfect. A main difficulty is that we primarily get qualitative results, and interpreting and quantifying images requires expertise. However, here's the exciting part. Technology is rapidly evolving. The challenges we face today are becoming tomorrow's solutions. The progress in information technology, the image processing, the artificial intelligence, and the deep learning networks have boosted their interpretation, and they are bridging the gap, making NDT more quantitative and much more attractive. Thus, despite the learning curve, with the right training and understanding, NDT offers an unparalleled level of insight and control in the restoration process. Our comprehensive evaluation methodology involves several stages. First, we conduct a thorough initial diagnosis using non-destructive and, if needed, the analytical techniques to understand the artifact's materials, construction, and current condition. Next, we apply both traditional and innovative green materials under controlled experimental conditions, including aging on mock-ups where necessary, to accelerate the degradation phenomena and simulate real conditions. Finally, we reevaluate the artifact using the same diagnostic methods to compare its post-treatment state with the initial condition, providing a comprehensive assessment of the green material's performance. To ensure the GREENART project's findings are directly applicable to real-world conservation challenges, our studies utilize both representative mock-ups and carefully selected actual artifacts. These sacrificed, let's say, pieces, chosen for their typical characteristics within specific categories, allow us to test materials under realistic conditions. For instance, easel paintings with significant dust accumulation are employed to evaluate surface cleaning effectiveness. This real-world testing is essential for validating and practicality of our green materials and identifying potential issues before market release. We've selected 18th, 19th, and 20th century artworks that are representative of the challenges faced by Greek conservators and that exhibit complex structures and material properties, making them ideal for our studies. A multifaceted approach was used to evaluate the assess the outcome of the applications using the GREENART materials. As stated before, the methodology included non-destructive techniques, namely imaging techniques, but also colorimetry, glossimetry, and inno-light digital microscopy. If required, these methods can be assisted. They were being assisted by ATR-FTIR analysis and portable XRF analysis or portable Raman analysis in case a more accurate material identification is needed. To truly understand the surface of our materials, we rely on a range of powerful imaging techniques. These methods essentially capture how the layers of a surface interact with electromagnetic radiation. We're talking about light, but in ways that go far beyond what we can see with our naked eye. We employ high-quality cameras, both standard DSLRs and advanced hyperspectral imagers to do this. This tool allow us to visualize the surface in several ways. For example, we use ultraviolet-induced visible luminescence, or UVL, to reveal hidden details by exciting the surface with UV light and observing the resulting visible glow. We also capture images in the visible and near-infrared spectrum using different lighting modes like reflecting, transmitting, and raking light, as well as the monochromatic and epichromatic imaging to highlight subtle variations in texture and composition. And for the most detailed analysis, we acquire spectral cubes. These are essentially data-rich images that contain information about the surface reflectance across a wide range of wavelengths, allowing us to identify and map specific materials and their distribution. In a sense, these imaging techniques provide us with a comprehensive and nuanced understanding for the surface, revealing information that would otherwise remain invisible. Some photos of the setups were used, you can see here. Okay, in this slide, in the next slide, you can see a series of images captured using different setups: visible IR, UVL, the point spectrum produced by the spectral cube, the dino light images, as well as the XRF analysis. Now, all right, let's see some examples, and let's begin from metal coupons. Visible inspection of the surface of the metal can be tricky. Depending on the angle of observation, the surface can be lighter or darker, glossy or matte. If you do not use a soft box, effort should be made to light the object uniformly to avoid ambient reflections. Ultraviolet-induced visible luminescence can prove to be very helpful in monitoring metal objects. Metal surfaces usually absorb UV radiation and do not produce any fluorescence. Unfortunately, some conventional coating materials, such as beeswax and incralac, you can see in the image in the left, exhibit similar behavior and do not fluoresce. However, new green materials, as you see at the right, exhibit fluorescence. Differences in intensity and color of illumination can be indicative of the material used and of the degradation of the material. Handheld digital microscopy can prove to be very helpful in the examination of the surface and the coating of metal surfaces. While visible inspection can record the object's surface, usually coatings are colorless and transparent. They could be potentially located in the rare cases where coatings are not evenly distributed, and differences of the morphology between metal surface and coating surface can be observed. Therefore, closer inspection provided by the handheld digital microscope can be of assistance. Uncoated areas reveal microstructure constituents like etching, surface oxidation, for example, the green color of Quai, and environmental deposition, for example, whiter hue from salts. Coated areas may present different color or glossy behavior. The general rule and majority of degradation phenomena on organic coatings tend to decrease and eliminate their thickness. Our thickness measurements are based on electric resistance of a non-conductive coating on a conductive metallic sample. Either organic coatings or oxidation product films are commonly non-destructive materials, and in this way, you can estimate their thickness. In this respect, thickness measurement can assess in a second order, after optical inspection, the condition of coatings. However, one should monitor thickness alteration because the coating may be disappeared and oxidation phenomena film of the metallic surface may be developed. For example, specimen 0, you see at the right, the uncoated metallic sample presents increase of its thickness due to oxidation after 2 weeks artificial aging. On the other hand, beeswax coated sample presents total coating consumption, and finally, some underdevelopment coatings, biopole series present increase, and this fact may be oxidation phenomena indication locally or entirely, and need, of course, further examination. When we analyze color changes and quantify color alterations or possible aging impacts on the samples, there are a lot to consider. However, for a quick and practical overview, we often use the delta E calculation. It's essentially a measure of the overall color difference, and you can see the formula up here on the slide. Delta E takes into account 3 key parameters: the difference in lightness or darkness, represented by L and delta L, the difference in red and green, shown as A and delta A, and the differences in yellow and blue, indicated by B and delta B. Simply put, a larger delta E value signifies a more significant color change. And if the change is substantial enough, we then can see it with the naked eye. Take, for instance, our 0 sample, code 0 sample. The uncoated metallic, the uncoated metallic bronze. Its delta E value is remarkably high. And if you look at the comparative photos, you'll see that what we observed visually aligns perfectly with the colorimetric data. The whiter hue I mentioned earlier is evident in the photo on the bottom right. Now we also notice some localized stain-like features. These appear to be related to microstructure reactions between the metallic bronze and its environmental, a case that is currently studied in our team via microscopy and microanalysis techniques, optical microscopy, and SEM EDS, actually. Now, let's dive into the results from the glossimetry evaluation. We have encountered some fascinating, though complex, behavior, which is really highlighting the various degradation processes at play. For highly reflective surfaces, like our polished metal samples, we typically access glossiness at the 85-degree angle. And what we're seeing, in general, is a decrease in glossiness over time. Look at this graph. The blue lines represent our unaged samples, and the red lines, the aged ones. You can see the downward trend. This reduction in glossiness points to micro and nanostructure changes happening within the organic coating. However, it's not quite that simple. We've also observed indications that moisture absorption can temporarily increase glossiness. And it's a bit counterintuitive, right? But it seems the moisture is having a temporary smoothing effect or altering the refractive index of the surface. And then there is the extreme case, when the coating is almost completely gone, essentially disappeared. In these situations, the glossimetry reading actually, the glossiness reading actually increases. Why? Because the metal itself and any thin oxidation layer that might have formed is now exposed, leading to higher reflectivity. We are still actively working to fully understand these nuances. Let's see another example coming from 2 panel paintings which were selected from the early 20th century. One of them is depicting Archangel Michael, with the other one is depicting Holy Trinity. Both were made following similar techniques, using a textile support, a preparation ground layer, a tempera, and a varnish layer for protection. 2 kinds of tests were carried out: surface dirt removal and varnish removal. For the surface dirt removal, a series of hydrogels were tried out, loaded with an aqueous tack solution, 2% for each area, gel, 365-minute application took place. In between application, dry cotton swabs or peggy gums were used for dirt removal. After all the application, a rinse with peggy gums took place. When we are evaluating cleaning methods, especially on delicate surfaces, we need precise tools. We started with UV fluorescence photography, which, as you can see, in the second image at the left, give us a good initial sense to dirt removal. Brighter fluorescence generally indicates a cleaner surface. For instance, notice the clear difference with the PEGI 6 application. It shows a significant reduction in dirt. However, UV fluorescence isn't always enough. When the differences are subtle, like here, CPVA AD and PVA SA, we need a more sensitive method. That's where colorimetry comes in. Colorimetry, by measuring reflectance and calculating the delta A parameter, allows us to quantify those sub-differences. I don't have an example of this, no. Okay. Now let's talk about varnish removal. We aimed for a green approach utilizing organogels loaded with acetone and a 1:1 acetone ethanol mix. To ensure a clean starting point, we first pre-cleaned a horizontal section with PVA-SA hydrogel containing 2% TAC solutions, effectively removing the surface dirt. Then we applied our organogels vertically, covering both this pre-cleaned area and an adjacent and treated section. We opted for the successive 1-minute applications for each gel. I'm finishing. Looking at the uncleaned area, the results were quite noticeable. Both the acetone and the acetone ethanol mixture visibly altered the surface, as evidenced by our visible and UV fluorescence imaging. However, on the pre-cleaned area, the changes were far less dramatic. This is where the power of digital microscope came into play. As you can see the image on the left, taken at a close-up scale, the varnish removal was neither uniform nor complete. But if you look at the images on the right, the varnish is almost entirely gone from the same close-up view. In conclusion, our work in the GREENART project isn't just about testing materials. It's about empowering conservators with innovative, sustainable tools. We at least try to bridge the gap between cutting-edge research and real-world application, ensuring that our cultural heritage is preserved for generations to come. Thank you, and I'm sorry for being long.
Thank you. Now we'll have Balázs Lencs. There are two authors. The second one is not here, Norbert Nemeth. Lencs is head of conservation of the Hungarian National Museum and 14 affiliates museum or institutions. And he collaborated with several projects, green project, European project, like Apache or Aurora. And his research focuses on metal-based lacquered oriental objects. And he will present us now the evaluation of green materials developed in GREENART project used in the treatment of historical objects at the Hungarian National Museum. Thank you.
Good afternoon. Thank you for the introduction. First of all, I'd like to express our thanks that we can be involved in this wonderful project. Although we are very small, tiny wheels of this huge machine, we're trying to do our best according to our capabilities. I was dreaming to present you more results for this presentation, but most of our tests are still going on and need to be assessed. And one last thing that my colleague Norbert Nemeth has some private issues, so I will present you this presentation this time. So, first of all, I would like to introduce you the National Museum, which is now officially Hungarian National Museum Public Collections Center, which is a kind of cultural conglomerate of Hungary, incorporating 6 major museums of Budapest and 35 regional institutions and visitor centers. And the National Museum, the H&M itself, is responsible for the collection and all the scientific work of objects connected to the history of Hungary from the Neolithic ages up to present days. We have more than 3.8 million objects in storage inside of the museum building and outside depots, and only approximately 12,000 objects are on display. And we have significant archaeological collections, musical instruments, and other major collections. I would like to show you some pictures of the main building itself, the interior, and some of the pictures from the exhibitions, from the archaeological exhibitions. And we have a Roman stone lapidarium and a historical exhibition, archaeological exhibitions. We have even modern age objects like the BMW motorcycle, and the most important piece of the museum is the holy coronation mantle, which was, according to the legend, was worn by the first Hungarian king. I would like to introduce you the conservation department itself. We have the standard activities of a conservation department. So we do preventive conservation and remedial active restoration, the maintenance and innovation of storage and exhibition devices methods. We do scientific research, and we do the supervision of and active work on exhibitions. For example, the establishing of environmental conditions, producing condition report installations, and so on. Sometimes we do special packaging for storage and zone, and we're creating protocols for the treatment and handling of artworks. And a very important part of our work nowadays is the making of the copies and replicas of original artworks. And of course, we disseminate all the knowledge we acquire during our work. The conservation department brings green methods into conservation practice. For example, the recycling of used materials and application of gels, replacing harmful and toxic materials. On the right, you can see some pictures we did recently. We reused the waste material of cleaning, and we made some coasters for laboratory utensils. It's not only for recycling the waste material, but it was also for the promotion of the green approach, of the green thinking, to the not only for professionals, but also for the society. And also what we do inside of the project is we provide relevant artworks with different composition and condition, and also did some mock-ups for the testing. And we use remedial interventions of the new material on the case study objects, and we monitor and evaluate the results. And of course, we will disseminate and gain knowledge on different levels. And since the H&M has on reused infrastructure of technical instruments, so we cooperate with other institutions within the GREENART. And as told you before, we provide some case study objects. But first of all, we involved in different working packages, actually 5, working package 2, 3, 4, 5, and 7, and we provide these objects. Let's go through these objects. The first one is Handstein, a so-called Handstein, which is a model of a mine with gilt silver, and crystals and minerals are on it. I will talk about it later. There's a leatherette bag from the 20th century. It's a modern age object. There's a bonnet with metal lace, World War I Austro-Hungarian troop badges, which are made of mainly zinc-based alloys, and a nobleman's sword belt from the 19th century. Let's go on to working package 2, which is about the cleaning. So we are involved in task 2.3, and as a preliminary preparation for the trials, we did some tests with the traditional materials we use in everyday practice. on the sword belt, for example, and these are including the mechanical, cleaning with detergents, using mild acids, some gels, some silver dip, and triammonium citrate, and also local electrochemical cleaning. We also tried to use our new novel device. It's also kind of green cleaning method, which is called the Pleco. It's developed by a Swiss institute, and it's designed for the analysis and the removal of corrosion products. So we tried this device also. It's kind of for a kind of preparation for the comparison of the green, for the effectiveness of the green solutions. And prior to cleaning trials on the case study objects, we performed 60 pieces of copper coupon test with the new hydrogels, and which is still in progress. These are half matte and half polished coupons, and we applied onto them the most common coatings we can find on our objects from the storage. They are modern and also historical coatings, as you can see. So we used polyvinyl butyryl, Movolate, Perolate 72, Incrolac, and B67, and also Damar varnish and shellac varnish. So these were some of the results we could get. It's really hard to see on the screen for me, but as far as I remember, we loaded the different gels with the nanofluids, and for the examples you can see here is a PVSA type of gel, and we also use the benchmark for this cleaning, which is polar coating B. And the most effective, because they were really effective, some of them, of the new green materials, was the diethyl carbonate, the DEC type of nanofluid. We put these coupons after the removal into high concentration of hydrogen sulfide vapor, so we could clearly see the differences and the effectiveness of the cleaning of the gels. But on the other hand, during the removal of the Incrolac, we could not observe any effectiveness of the new green materials. It's also a kind of result, and it was interesting to see what happened. Then we moved on to the cleaning tests onto the provided case study objects in the real case scenario. The problem in these two cases is that the original artworks does not have a heterogeneous grime dirt layer. So, but during the cleaning trials, we tried to find more or less the same appearance of contamination on the surfaces, so we could compare the effectiveness of the different materials. First, we tried the cleaning fluids on the nobleman's belt, and in this case, because of the complex structure of the surface, we did not use the gels. Instead, we tried the nanofluids with swab cleaning, and in this case, two of the nanofluids were effective. We could observe the diethyl carbonate and the butyl acetate types. You can also, maybe you can see not so clearly the differences before and after treatment of 1 minute. And of course, these materials removed this grime dirt layer, but some of the corrosion products which were embedded in this grimy surface contamination. In the case of the Handstein, we used, because I told you there are crystals and minerals on the surface glued with, originally with animal glue, but afterwards it was repaired with several different materials anyway. So we had very complex structures. For example, in the surface of the crystals, we used the cellulose pulp, a type of cleaning method. We put cellulose powder into a Japanese paper and then wetted this kind of pad, and they pushed it onto the surface. And as you can see, I hope you can see, it was effective. On the surface, there was a kind of whitish contamination, and after the treatment, it showed a very nice result, and it's very promising. And in this case, the diethylketones and the butyl acetate showed very nice results. There are some organic decoration parts on the object, for example, small leaves, which are painted green, not really visible for the first time, but with closer look you can observe. In this case, the most effective nanofluid was also the diethylketones. In this case, we could use the gels. Let's move on to working package 3, which is about coatings. First of all, I'd just like to mention that sometimes we are faced with the problem of producing even surfaces, coatings on large polished objects. We always try to avoid of making iridescence, undulations, and opalization of the coating. So we performed some spray coating tests, and it was also kind of preparation for the green materials because we are planning to do some spraying tests also with the green coatings. And so we established a kind of validation protocol for the coatings. Just quickly just run through. It's also 60 pieces copper coupon test and 10 pieces silver coupon test with the half matte and half polished surfaces. We prepared the tube badges. We will apply the coatings, as I told you, in different concentrations and also with spraying techniques. We will then test these materials, and we'll have visual observation with microscope in UV also and 3D documentation, and we will use some corrosive exposure with hydrogen sulfide, formaldehyde, acetic acid, which are the most common off-gassing materials in our museum environment, which is not so good, but that's the reality. And we will measure it with colorimeter and glossimeter, and we will also use some artificial aging in our new artificial aging chamber, and we will do all the mentioned examinations with both intact and aged coatings. This is the schematic scheme of the validation protocol we'll use, just as I explained to you before. We're also involved in, as I told you, in working package 4.3, task 4.3. In this case, also Hanstein is involved, and the leatherette bag. First, we established our requirements for these storage enclosures, and we are in close contact with the ZFP, with Manfred and his colleague with Katrina, and we already received these new boxes, which are very good, I can tell you. Manfred told us about their airtightness, and I can prove it. I can say that they are really airtight. Actually, it's very difficult to take off the lid. I told Manfred before, you get to have very hard hands, but anyway, that's really good. And also, these novel adsorbers developed by the Fourth are also installed into them. And these objects, these storage boxes, together with the leatherette bag, are now at the Ljubljana University, and they are under examination. The measurement of the VOCs emitted by the object itself, the leatherette bag, because now it's in a very, very accelerated aging phase, and they will test the effectiveness of the adsorbers and the materials of gassing. And finally, working package 5, task 5.3. So we have selected and verified exhibition spaces, storage areas, and outside depots for the sensors locations. Besides of the storage boxes of the case study object, test chambers are also prepared. And following the on-site measuring and evaluation of the selected areas, we have to reconsider the requirements for these sensors. And we just not so long ago received this green sensor from the fourth. The base of this sensor is made of cork. Yes, I will just one more slide. As you can see, as I told you, these sensors will be placed not only into the exhibition areas and some storage areas. This is the storage of photographic collection, but also to outside depots where the environmental conditions are very harsh. And as we heard in the morning session that there are hard tests and hardest tests, it will be kind of hard test since in these outside depots, even if it's the Hungarian National Museum, we don't have proper air conditioning, no heating in the winter, no cooling in the summer. So these parameters are fluctuating in very extreme ranges. So we also communicated this to the sensor developer parties. So, and of course, we will compare the results of the sensors with our benchmark equipments, and on the basis of these results, we can go on. And that's it. Thank you very much indeed.
Thank you very much for for all of you. Now we'll take 15 minutes for time for questions if you have in the room. If you have any question, please raise your hand. Ask for the micro. Yes, there is one here. Please present yourself before beginning to talk.
Hello, my name is Kinga Kremińska. I'm PhD student from the University of Nikolaus Copernicus in Toruń, Poland, and my thesis is related to synthetic binders in Polish paintings, and I have questions from Branly Ormsby. If in Bridget Larry paintings is preparatory to drawing visible, and if yes, do these parts require different cleaning approach?
Are you asking whether the pencil was visible?
Yes.
Absolutely, 100%. And we tested that with mock-ups with pencil, and we tested on the painting, and the gels had no effect on the pencil.
Okay, thank you.
Is there another question to the panel of authors? Okay, I will have one at least for all of you, because I wasn't here this morning, but I was wondering, and I think you talked about that at the beginning of your presentation, Mr. Baglioni, about the life cycle analysis of the products you are testing. I understood, but I just wanted for the room to be sure, if I understood correctly, you also take in account this aspect of the product you're testing, or it's not?
Yes, we do. There was a speech in the morning from Venice, from Martina Delga, which talked about the methodology we use.
Okay, so every time you're testing a gel or component, you will try to know its life cycle analysis? Or?
Yes, all the materials that are at the end should be, if you want to use it, it must be validated by the analysis.
Okay. Someone has another question, because I have another one, but I would like to leave the... No? I was curious about this project, this 3 years project, and if you know the Go Green project, which is also a European project. What do you have connection, all of you, with this? Because it's also defining green conservation, and some subjects are cross, or it's what would be the difference?
Okay, they use a different approach. So they are trying to define a methodology for conservator. So in order that conservator, at the end, they can have an idea of what they are using and what is green or not green, more green or less green in their activity. We are making the analysis on products and methodology. So our analysis is more classical, in a certain sense, but even more sophisticated. At the end, we define if a compound or if a methodology is green or not. Then, if you use in the good way, it can be still green. If you use in the bad way, it cannot be. It could be less green. So this is green. The other one.
Go Green project.
Go Green.
Yes.
But we have a cluster. So we establish a cluster between 3 projects and 3 more projects in informatic intelligence, artificial intelligence, so on, for methodology and materials for conservation. So this cluster actually was promoted by European Union and will be a cluster that will be present in the new partenariate among states. So they're defining new partenariate, and the European Union is promoting this new partenariate. So France actually is the leader, so is the partenariate are in charge of France. So Italy is participating, and many other countries are participating. So, and within that initiative, there will be something related to this clusterization. And this is useful because otherwise you spread money in too many directions, so it's better if you keep in the right way.
Okay, thank you. Yes, there is a question here in the middle, 3rd row. No, I think it's better with the micro because if it's recorded, and present yourself, please.
Alessandra Cava, introduced myself already in the morning, studying at the ICPAL for the Central Institute for Paper and Book Pathologies in Rome. And I have a question, it's a technical question for Professor Baioni. I'm interested in the nanostore paper products of your company, and I was the CCGI, and I was reading that you have ethanol 5% based treatments for deacidification of paper, and we have the experience of the standard calcium hydroxide, not in nanoparticles, with a maximum solubility of 3 to 3.5%, 5 grams per liter, while you go to 5. How do you do that? It's because of the nanoparticles, because obviously, if you treat it, it would be enough to have 1 treatment rather than 2 that we usually do for the alcohol deacidification.
Okay, just to be precise, I have no company. I'm a university professor,
no,
so
well,
this company belongs to the university and
Good.
not to me.
Okay.
And then we use a non-aqueous deacidification system, and we use nanoparticles. In principle, we can go up to 60, 70 grams per liter. There's no problem on that, because you use a different aspect. So you use free calcium hydroxide in water.
Yes.
We use nanoparticles, so the fate, is completely different, because you use a wet, say, deacidification. We use a solid state deacidification, where the deacidification goes through electron holes in paper. So we don't use hydroxyl that move around the paper. We use electrons that jump from one position to another one without water.
Yeah, that's interesting.
So it's a completely different process.
Yeah, thank you.
Someone else?
Discovered by Linus Pauling in 1944 for water. definition of pH, 1944. Long time ago.
Anyone else in the public? Yes.
Elena Aguado. I'm an educator from Madrid, Spain, dealing with paintings and cleaning too. And my question is for Dr. Ormsby. When it comes to the design of intervention cleaning in this case, and particularly polyvinyl acetate paintings, how long, if you can say, does it take to make the state of the art of the properties, composition, and behavior of these materials before you say important to know the artistic entity of the work of art, but also properties, composition, and behavior of the material, state of the art?
Have I understood your question? How long will it take to understand those paints and their treatment risk? Is that what you're saying, Elena?
Reading other people.
Oh. Are you asking how long it took us to understand enough to proceed with the treatment in terms of risk?
Yes.
Maybe. Well, we spent time, we did the literature review, which was always helpful, and hopefully that's helpful for other people. That's one of the joys of being in a government institution. So we can't know everything, and each paint is different. And to be honest, the PVA paints in Bridget Riley's paintings were more robust than we expected, because PVA paints generally are less cohesive and have more, they're less weathering power on the whole. So I guess it's hard to say, because I've been looking at these paints in different ways for a really long time, so I don't know how much is kind of in my bones, if you know what I mean. But yeah, I mean, it took us a while, and we're still discovering new things, of course, but when you are faced with a treatment and you decide to go ahead, you inform yourself as best as you can by reading, by speaking, by considering and working with people. I don't know if that answers your question at all, Elena.
Absolutely.
But, it takes time, but also there's, I need to choose my words carefully, informed choices, and there's also acknowledging there are things you don't yet know, but you still proceed with that knowledge if the painting responds in a way you consider acceptable. And for us, the risk turned out to be quite low in applying those cleaning systems to that particular painting. There are other artworks in the collection that the risk would be higher, and we would choose not to clean. But with all your, if you like that expression, all the ducks were lined up in a row, we were very happy to proceed. And that's a collective decision. It wasn't my decision. Hope that answers it.
Yeah.
Happy to chat more.
Yeah.
Thank you.
Is there another question? I can't see any hand. No? So maybe it's time for a coffee break? Hopefully. Thank you very much.